In our previous video, we saw how questions about the existence and uniqueness of solutions to a linear equation in linear algebra are connected with questions about the span of a set of vectors and the linear independence of a set of vectors. The next step that I want to take is getting us a little bit closer to thinking not just about a matrix as an object that we can multiply by, but thinking about the ways in which a matrix determines for us a function, where we give input to that function by supplying a vector that matrix can multiply by on the left, and the output is then the result of multiplying that matrix by that vector. So every matrix defines a function in this way, and we can study properties of those functions by looking at properties of the matrix, because some of the most important properties of a function relate to the existence of solutions to equations that function defines. Those are questions about the range of that function, and uniqueness of solutions, which are really questions more about how the function behaves in its domain. So let's take a quick look at what I mean before we get back into this chart. Suppose I think about the matrix 2, 1, 1, 1. This is a matrix with 2 rows and 2 columns. And what that means is this is a matrix capable of multiplying a 2-dimensional vector on the right of it. Right? A can multiply by a 2 by 1 vector. And so the domain of the function that this defines is going to be 2-dimensional space, R2. It's this purple plane. I'm thinking of this purple plane over here as the domain of my function. And how the function works is that if I supply a vector, say 2, negative 2, and I multiply this matrix by that vector, the result is going to be another 2 by 1 vector that lives over here in the codomain. So this copy of the xy plane I'm thinking of as where the outputs of my function live. And if I supply the function with an input of 2 minus 2, then the output it gives me is this matrix times 2 minus 2, which in this case is going to be 2, 0. If I give this matrix a different input, it's probably going to give me a different output. But I say the word probably there for reasons that I hope we'll be able to appreciate in this video. So the question about the existence of solutions to this associated linear equation is really a question of, if I pick a vector in the codomain, if I pick a vector in the green xy plane over here, can I find a vector back here in the domain such that A times that vector gives me the vector that I chose on the right side? So if I set myself a target, let's say I choose a vector over here, maybe 2, 4. Is there a vector in the xy plane which, when I multiply the matrix by that vector, it gives me 2, 4? And in this particular example, the answer is yes. That vector is minus 2, 6. And it just so happens for this matrix that it looks like any vector that I choose on the right side, any green vector that I pick, is going to have some purple vector in the domain, which when I multiply the matrix by that vector, it gives me the thing that I'm looking for. So in this example, it looks like this equation, ax equals b, is always a consistent equation. No matter what right-hand side vector b that I choose on the right of my screen, there exists some solution, x, on the left-hand side of my screen, such that ax is equal to the b that I chose. So that's really cool. Let's layer some terminology on top of that we've already been using. First of all, we say that the column space of a matrix consists of all of the vectors that I can get by multiplying A by any vector x. So if I take and somehow could stuff all possible values of the vector x into my function, multiply A by everything in the domain, then the set of outputs that I get is what we call the column space. And evidently in this example, I can get any vector in the green codomain on the right by multiplying A by some purple vector. So what that means is that the column space of this particular matrix A consists of all vectors in the xy plane. And another way that we're going to say that in this video is we can say that the span of the columns of A consists of all of the xy plane, R2. Another way to do that is to say, using span as a verb, that the columns of A span R2. That's just another way to say that I can make any vector in R2 as a linear combination of the columns of this matrix. That also, you'll notice, shows me that to solve this equation, ax equals b, the solutions that I get are going to be unique. there's only one vector on the purple domain here, which when I multiply it by this matrix gives me the vector that I want over here on the right. So if B is the vector 2, 2, for example, the only vector x for which A times x is equal to 2, 2 is the vector 0, 2. There's no way to make another solution to this equation. And we can see that by taking my green vector on the right-hand side and asking, well, what if that green vector is just the 0 vector? What if my goal is to understand which vectors A multiplies and sends to 0? So what are my solutions to AX equals 0 going to look like? That's, remember, what we call the homogeneous equation for this matrix. Which vectors is A killing? Which vectors is A sending to 0? And evidently, in this example, the only way that I can take a vector in my xy plane on the left and multiply it by A and get 0, the only way is to have selected the 0 vector in the first place. So the set of solutions to the homogeneous equation in this example consists only of the 0 vector. The 0 vector is the only vector at all which I can multiply by A and get 0. And so this is a point at which you might pause and ask, well, isn't that always the case? How is it possible that there might be other vectors which when I multiply them by A, I get the 0 vector as the result? For this matrix, it doesn't happen. And so the set of homogeneous solutions, in other words, what we call the null space of this matrix, consists only of the 0 vector. But for other matrices, that might not be the case. Let's consider this slightly different matrix, 2, minus 1, minus 2, 1. If I ask what are the solutions to its homogeneous equation, which vectors does A send to the 0 vector, clearly one answer is always going to be the 0 vector. A times the 0 vector is going to give me the 0 vector. But if we start poking around in the domain over here on the left, we'll find out that it's possible to choose, evidently it's possible, to choose a purple vector in my domain, which gets sent to the 0 vector, but which is not itself the 0 vector. A is killing some things which were not already the 0 vector in this example. Specifically, I found a vector here, 1, 2, such that A times 1, 2 gives me the 0 vector. So this matrix has a non-trivial and non-zero vector solution to its homogeneous equation. 1, 2 is getting sent to 0, 0 by this matrix. And you'll also notice that that means that other vectors are also getting sent to 0, 0 as well, such as 2, 4 and negative 1, negative 2. If I can dial that in just right here. Negative 2, negative 4. So there's a whole bunch of vectors, evidently, from my domain, which when I multiply them by this matrix are becoming 0, 0. So now the homogeneous equation has a bunch of solutions in it. There are a bunch of vectors which when multiplied by A give me 0. And so when we layer our terminology back on top of that, that means that the null space of this matrix is not just the 0 vector. It consists of an entire, what we say, vector subspace. In this case, it's a one-dimensional subspace or line. There's an entire line going through the origin such that every single vector along that line gets sent to 0, 0 when we multiply by this matrix. So the null space here is this entire line of points. In fact, it's the line y equals 2x in this example, of points passing through the origin, and all the vectors on that line are solutions of the homogeneous equation. That's very different behavior than we had with the first matrix that we saw in this video. So that's what can change about the null space. But now that the null space has changed, we'll notice that something else has changed as well. For example, if I pick a different vector, let's say I pick the vector, I don't know, minus 2, minus 2 in my domain. If I multiply A by that vector, the result is going to be the vector minus 2, 2 in the codomain. Right? A times this vector is going to give me that vector. But what is the set of solutions? What is the solution space, not to the homogeneous equation, but to the equation AX equals this vector? What does that solution set look like? Is minus 2 a unique solution to this or not? And what you'll notice is that there's actually a bunch of other vectors on the left-hand side that I can choose here, which when I multiply by A, I can get minus 2, 2. In addition to minus 2, I could also have chosen minus 1, 0. That's another solution to the equation ax equals minus 2, 2. I could also have chosen 0, 2. And that's also a solution of this same equation. So what you notice is that now the solution space of my inhomogeneous equation is not unique, but it also consists of an entire, what looks like an entire line's worth of points. And the reason that that's possible is that when the homogeneous equation has infinitely many solutions, that also means that every other equation that this matrix defines will also have infinitely many solutions. So because my null space for this matrix, the homogeneous solution set, was an entire line, it turned out that my solution space for any other system is also an entire line. And it just so happens that that line, the solution space of the inhomogeneous equation, is parallel to the null space, the solution space for the homogeneous equation. So I no longer have unique solutions for any equation that this matrix defines, because its homogeneous equation doesn't have unique solutions. And finally, we'll notice one other thing about this matrix. What about its column space? When is the equation ax equals b consistent at all? When do I get a solution at all for this system? Clearly, for the vector b equals minus 2, 2, I get a consistent equation. I get a whole bunch of solutions that all lie along this line over here. But what if I pick a different vector in the xy plane to try and use as my right-hand side b? For example, what if I chose the vector 2, 2 again? Do I get a consistent system? And the answer is no. We can't find any linear combination of the columns of this matrix that give me 2, 2. And so ax equals b is inconsistent. Its solution set is an empty set. So two things happen simultaneously for this matrix that contrast it with the first example that we saw. The first thing that we noticed is that the homogeneous equation, the set of solutions to ax equals 0, was no longer a single point. There was no longer a unique solution, but there was a whole infinitude lying along a line of solutions to the homogeneous equation. The null space was not just a trivial set with only the 0 vector in it. But simultaneously for this matrix, we also destroyed the column space. The column space used to be the entire xy plane, but now we see that there's a bunch of vectors that don't live in that column space. The only way to make this system consistent is to choose a right-hand side vector that lies along this green dotted line over here through the origin. The column space of my matrix, the range, the set of b's for which this equation is consistent, is not the entire xy plane anymore, but it's just this line. And it looks like the line y equals minus x. Why? That's exactly the line which is the span of the columns of my matrix. But the two columns of my matrix, minus 1, 1, and 2, minus 2, that's this vector here and that vector there, those vectors were parallel to one another. So when I take their span, they don't span R2, but they only span that line along which they both reside. And so the column space of this matrix consists only of that line, which means the only time that that equation is consistent is if my right-hand side vector is chosen to be a vector that lies in that line. So this is how we think of a matrix as defining a function, and we use the column space and the null space to discuss the properties of that function. In our next video, we're going to return back to our big diagram of the theory of the first half of our course and connect these questions to questions about span, linear independence, and the invertible matrix theorem. So stay tuned for part 3 of 3.